This is an example of Newton's third law. For every action, there is an equal and opposite reaction. So in this situation, as the car exerts a force on the ball exerts an equal but opposite force on the car.
So this right here is an example of Newton's first law, where a body in motion stays in motion, and as the car goes left, the ball wants to go in the direction it's going, which is straight, and that's why it goes across the seats.
Watch out! Stop sign!
So this is an example of Newton's first law of inertia, where a body in motion stays in motion. Since Dylan's not part of the car, when he starts to slow down, the car is slowing down, but he isn't really. That's why he keeps going forward.
This is an example of the relationship between gravitational potential energy and kinetic energy. I have gravitational potential energy at the top of the hill, but as I'm going down it, it's slowly converting to kinetic energy. This shows how energy cannot be created or destroyed. It can only be converted or transferred. So the units for gravitational potential energy is your mass, or the mass of the object, times the gravity times the height of the hill. And then kinetic energy is 1/2 meters, or 1/2 mass times velocity squared. So say you're trying to find the velocity, you can use the formula gravitational potential energy equals kinetic energy. And so say my car weighs 30 kilograms and the hill is 40 meters high. Then if I want to find the velocity, I can just cancel out the masses on each side of the equation, and my velocity squared would come out to be 784 once I solve for it. I just square root that and I find out that my car was going 28 meters per second. So this is an example of centripetal acceleration. In this, my car, as you can see, is going on like a curved path. The force of my car is directed towards the center of the path I'm on. That's why that makes that curve. If I were to keep going on this path, it would make a complete circle. So in this graph right here, my car is going in this direction because my force is directed towards the center. That's why I'm not going off this line right here. Great, now my car's broken down.
So your car's in my driveway. You think you can move that?
Yeah, sorry, I'll push it right now. So in order to move the car, I needed to break the threshold of static friction first, which takes more force to do so. That's why it looks like I'm struggling. But once I break that, once there was enough force, it turns into kinetic friction, which takes a lot less force to keep it moving. So like in this graph, you see my force building up right there. And once there's enough, the static friction turns into kinetic friction, which is right here, and it takes less force to keep the car moving. Hey Tom, so my car broke down, so I don't think I'm going to be able to make it into work. So I'm fired.